clean up my screen at least a little.
It's too late for
That's,
that, Bob.
um, let me, let me just put this one down for the moment. Come back to that. And I don't need to go to the agenda here. Everybody's got the agenda, but here's where I am with my notes and my notes from Brad's talk. And then I'll start here. And one of the things I think people know, okay, that saved everything. And by the way, this is my presentation job, so it'll be up on the screen. And one of the things is getting into this. Everybody here, and I'm communicating fine. Um, this uh, I hate. I can't get at the stupid. The Zoom thing is covering my that part of my screen. Um, anyway, getting down to um, the to CoSy. Um, One thing to emphasize is that in a sense the ultimate purpose of CoSy for me is just my everyday diary. One description's in Captain Picard's notebook, and so the focus more than anything else is on optimizing the efficiency for the individual, just simply as being a notebook. But also, I mean, if you're at the sort of person who's in a talk like this, it's being able to work through your thoughts, to express and work through your thoughts. And that's really why I learned APL to understand the geometry of multidimensional space through its algebra, is a way that I'd put it. So this was going to be basic array math in CoSy, and actually I got to so much that this is part zero, zero being the first number, the first address. So this is my first address on this topic. And most uses of arrays actually are in accounts where the most common use of it's interesting actually that this ties into this is Chris, I believe it is. There was a very interesting talk earlier at the hardware level. So a lot of people know matrix algebra and so forth, but main use of the dot product, which is and this is one of Ken Iverson's generalizations, is applying a function pairwise between elements of a list of a vector, and then another operation across them. But most common uses in ordinary accounting is the numeric use that pays the best. Um, and most typical sorts of most complexity you get into is units times price each, and the product and the sum of them, that's what your total bill is. But here, going to get into the geometric computations on Cartesian uh, coordinates. I mean, it's got, and as a matter of fact, you'll see. And incidentally, it was interesting to see another F8 here goes, and I wanted to get it over here. Let me, that's the wrong, I want to get it, I wanted to go and, yeah. Um, it was interesting that Julian Noble got mentioned earlier, but I met Julian at probably in Rochester Fourth Conference, but in any case, we had some talking about this. CoSy, in a sense, is again, it's generalizing from APL, but a lot of it is this general um, having it open. I've described CoSy as the shortest path from the chip to the math. And one of the points here is to be able to succinctly express the math. And I'd say that overall, and this is something that array notation and array algebra uh, does, is it's essentially you have sets of data and you have sets of functions, and you want to go and apply these functions to this data in sort of combinatoric manners. And but one of the things, and I will go and do, because I've done I answer a lot of things that come up on particularly LinkedIn seems to be what I get a lot of them. And then one of the things is go to the Techie Dome I've set up as a page where I go and I see, like, this was a challenge from LinkedIn. Um, Dialogue APL goes and on Mondays they give these challenges. What does this function do? And here is my answer is essentially this is the CoSy fourth that does this, and it turns out that what they're doing is they're determining whether an array. I actually have this um, over. Incidentally, something, this interface is one of the things that needs to be, replaced with a web interface. And I mean, a couple of things to go and make CoSy be commercially viable. But where were we? Techie Dome. Um, oh, I'll come back to that. But yeah, the triangular matrices. Just to go and here, this is an indication of where I have to delimit. This is the left argument, and this is the right argument. And you'll see that the take makes that a 3 by 3, a, a list of 3 lists, because that's the nature of the way um, uh,
But
AP,
Bob, why is that a take and not like a shape or something like that? I'm trying to connect it with the APLism.
um, because yeah, I don't know, history, just a path that it shape. I ran into the shape versus reshape in APL. And it's left whether it's something, whether you've got this the row is the shape argument and the reshape argument in APL. But it became, I mean, I'd written take. I mean, this is one of the things that is impossible to do. I defy anybody to do it in any other T-A-K-E colon. It's a colon definition, and this will go and find the colon definition, which happens to be in this main script. And here's all the non-blank. So here's the definition: modulo inde blah blah blah. Why I doesn't, well, okay, I do call it APL reshape.
You call out that in the comments, but not the. It's a strange choice of words. I'm trying to connect it in my head. Yeah. Anyways,
Well, hey, if you want to alias it, fine. You know, that's trivial. One of the things
fair enough.
actually in this fourth is, and I like this better than alias, although I guess it's slightly slower, but I can say you're going to have multiple colons. So okay, now I've got both definitions, except I'm not going to execute that. But it was a generalization of take. I mean, that's one of the things, and again, it's different than shape because shape, you know, you'll see the play with that earlier. But in any case, yeah, this was the you can compare though. This goes and um, uh, does this iota, of course, is that returns the first n numbers, and essentially, in any case, I actually factored that and into over here. Is this big enough? I should probably make this even bigger, and because there's nothing else to be. I actually split this into an upper triangular mask, and then whether, and this is identically equal. I think actually some of these words, um, but I don't want to get because you can work on this. Go to techie. Don't ask me questions. Put, you know, this is the thing is yeah, get back to me on that. I want to get back to, but one of the things is even this goes and shows that you have this array, this general array algebra. I wanted to get this more recent. This was this is actually something that, why is that just saying verbalists? Oh, somehow that seems to me to have gotten munged or something. But this is actually something in terms of this issue of of boy, something happened to that. Of the combinatoric application. I found this referred to an old comment that I'd made a long time ago that was very confusing to me, but because it concatenated, you can see this is okay. This actually is a word for no-op. It's just colon semicolon. It just is, you know, it does nothing. But here's a list of three functions. Here, this is the braces in Riva Forth goes and returns it as an unnamed function, essentially, as an unnamed verb. And here, for some reason, I had centigrade to Fahrenheit conversion. But this is making this construction here goes and executes everything in between. So you've got that xt. Essentially, this is a list of three xt's. And I just added a new word here, which essentially goes and takes those raw numbers and turns them into, returns it as an integer list. So there are the three xt's for those three functions. And this was from this old, you know, example that came up, and it was about actually doing well. This is what the original was about. It was about tipping, you know, how much you should tip. But I don't know what. In any case, here's a list of you know, the number of numbers, you know, and APV is an arithmetic progression vector. That's an old APL or IBM term. But in any case, I also made this, which, well, let me execute that. It just simply goes and is taking those integers and returning the raw values. And there are several iterators. This is doing it on each write. So this is essentially executing each one of those functions. This is the no op on it. This is multiplying by 1.5. And for some reason, this is turning the centigrade into Fahrenheit. Actually, something that is a good point in terms of, again, the use of CoSy is being just useful for my everyday, my tool. And I've recently, and the ability to have any line be an expression. I now in my workspace have this thing to convert centigrade, to give a table of centigrade to Fahrenheit. And the other day, actually, it got down to minus 24 here, centigrade. And actually, on the west side of the county, instead of the min for the entire state of Colorado was minus 34 that it got down to. Anyway, to go back to this, but in some sense, the ability to do this, and I also, as a matter of fact, recently just in following that, I kind of like that. Okay, when they talk about this is a centimeter to inch scale. So like right now, I can't see beyond the first set of hills here because it's kind of misty snow. But when they go and predict, okay, we're going to have eight centimeters of snow. Okay, that's 3.15 inches. And just to have that sort of tool around to just go and be an environment where I can do these things. Anyway, that's but this is actually being able to have a whole list of XTs and then apply that to some, again, you've got lists of data. I mean, the fundamental data structures are lists of lists. That's a significant simplification. Pythagorean triples came up, and hopefully it'll get to the right. And it's kind of long, but this got posted in a couple of different things. The whole, and I won't go through this, but I'll show because this is something you look at in XT, and then actually in a work log, all the work that I did on this was things. But getting down to this is all the code. Just point out this is all the code required to. This is all the Pythagorean triples up through. Oh, I don't know, up through all the numbers up to 20, I guess. And these are, like, and here you're going to see a lot of the 4, 3, and the 3, 4, 5 right triangle. But these are all the other values up to 20. And suffice it to say, this is more succinct than what was offered. So, but now getting to, yeah, that was it. Triangular matrices did that. The Pythagorean triples. And one of the things I want to point out that Bacchus, who also got mentioned earlier, in 1977, his Turing Award was he actually talked about Iverson having broken the von Neumann bottleneck, but pointing out that Iverson had rectangular arrays, rectangular and multi-dimensional rectangular arrays, and Bacchus in here points out, well, gee, you can just have lists of lists, and so what if they happen to be rectangular? Fine, but I'll point out one thing you'll see is there are the thing that gives, and these are the operators in APL or adverbs. These things that go and take a list, and the whole point in CoSy is you have this header that has, first of all, type, and second of all, the count, how many are in this list. A general list is type 0. So you can know your vocabulary that you're going to apply to things immediately from the type. But you have each monadic, and in an APL, that would be it just has a right argument, which is whichever way you're seeing it. And dyadic is it has, which would mean, and you'll see this, monadic means, okay, I have a list here, and I want to apply this verb, this function, to each item. Dyadic means, okay, I have two lists, and I want to apply this pairwise between each of the corresponding pairs. And list of lists, it actually, that'll be part one. But also each left and each right. And these actually really are, so far as I know, Arthur Whitney's inventions are in K. And Jim Brown, who is really the architect of IBM's APL2, was very impressed by how much they simplify things. It's very funny. You're seeing a lot of things glommed onto modern APL, which make it more closer to this list of lists paradigm. Actually, in some of those examples, there are, and these two are, this would be called a cross. Okay, I've got this list, and apply this function like plus across all the items of this list. So like, and the thing in brilliant in fourth and is just that you can just go, I mean, here. Well, here's an example. This is, and one of the things that actually, another those issues to go and make CoSy be marketable to ordinary humans is to go and genericize these operations so that don't have to say that it's a floating, just as plus. But, and I have genericized that right here. But you see, this is do a sum across. Okay, so that's sum, and we'll get to that. But to finish that, this final one, there are some others. You can make more, but this is scan in APL, and it's the same as across, but across just returns the single final answer. Scan goes and I guess Arthur, I think, could call it integrate. But so it will go and give, it'll return a list of the same length as the original list, and it's that incrementing across the list. So we're getting down to definition of dot. And I will get this, turns out this atomic application will be also in part one, but your dot product without that is really what we'll get to today, but essentially it's times. So that's pairwise. Dot takes two arguments, takes two lists, and it multiplies them pairwise, and then it adds across them. So, and yeah. So if I have, I want to show, okay, there's an integer list, and this is the thing, is this needs to be genericized, which these are actually some busy work, but well understood how to do these things. But here we'll be working on a 3, 4, 5 right triangle, very much, and this is dupe, but dupe with reference incrementing. So all it does really is make another reference to the object and uptick the reference count, which is the third item in the header, and so forth. So this is multiplying 3, 4, and by itself, making two copies, multiplying by itself, so they're square, and then and here's the brilliance of one of those brilliances of fourth, and where the RPN is really nice because okay, and this is one of those examples of a word actually looking ahead to in this case to go and parse it and return the XT of the word. So this is plus, a floating point plus, and a cross. So there's your dot product, okay? And it's the hypotenuse, the sum of squares. And one of the interesting things, no matter how many dimensions you've got, that's the squared norm. Let me go and just save that as, oh, here, and take the square root of that. Oh, this is another one of those things. It's so convenient in the RPM. I can just put the vertical bar and leave it forth. I really like as the comment symbol. So there you have. What did I do that? Oh, I know why. It doesn't like this double line there. Yeah. There's 3, 4, 5. That's the hypotenuse. Okay. Let me just save this as a temporary, so I'll refer to it. And I went through and showed this definition. Oh yeah, no, this is plus slash is so common that it's genericized, and this can be formalized and made into one place for use of external tables. But for a type 0, I mean, it looks at what the argument is, and if it's type 0, it says, oh, I don't know how to do that. Type 0 is generalist. If it's integer, okay, then it uses across I, which applies to integers. And if it's floating point, then it applies type F. So this is the general thing to go and make it so that and otherwise it doesn't know what to do. So it also says invalid type. But so I can go, and here's the basic definition of dot. Times pairwise between things, and then sum across. And incidentally, a word like, let me go and show this. This is a example. What have I got? Oh, I'm sorry. This is one of the reasons why I have to have an interactive environment. I'm such a lousy typist that I can't make any forward. There. Okay, now yeah. Yeah, there's the definition. This is actually the definitions of well, I got all of these together, the plus and signs and so forth. And these are actually right at these are the F87 or X87 level words, and what this each dyadic floating point resulting goes and turns that into something that like you see that's a pairwise. It goes and applies the thing pairwise. And that's built into, that's one of the most, this notion of atomic application is a very important sort of a thing, because again, it makes something as simple as times is just that. And so squared norm is just essentially something dotted with itself. It's the squared length of the vector. So I guess I still have T0 around. Yeah, it's at 25. 4 by 5. And norm, the length of the hypotenuse is just the square root of that. And one of the things is this applies, that's how you get the length of from one corner of a shoe block box or one corner of a room to the others. It's the sum of squares. And as a matter of fact, this is something that's rather applies to an awful lot of physics, is that computations are linear in the squares. Um, um, but so here I got T0 sitting around. Yeah, and it's sum of squares, which you see so commonly. Here I'm using this newly found construction to go and apply norm squared and norm uh, to each of those two things. So we're down to oh, okay. This is getting to the formation of average. And here, I've got the vector. Yeah, this is getting to the vector. Um, let me jump down. I was trying to make this so it follow my thoughts. Then again, no, I can't follow my thoughts. Let's see what I get. Okay, that's 1 divided by norm squared. Not sure that I think I might have gone beyond that. Oh, okay, okay. Yeah, that's a way to get the average. Actually, you've got this point 3, 4. I mean, this is one of those things. Consider this triangle 4. You out here 3, and here's this line, 45-degree line, the 1, 1 going through 1, 1. And what if all the numbers were identical? This is going um um no, that yeah, yeah, this is this has got the thing divided by its reduced in length, so its total length is 1. And I do, whoops, I didn't mean to do that. And yeah, 3.5, that's one way to calculate the average of the 3 and the 4, which may seem trivial. But that to go and do it, okay, this is duplicating it, summing it, and this is swap. I found that this was something I saw in some guy in fourth group on had used on a minimal language, but I really like getting swap is such a generic term that just simply having a word for it is swap. And this is the splat sign is count. It's essentially in an APL, it's like row, but actually they've added a new symbol which is the same as this in APL. And one of the things, again, because things are not genericized, I have to convert that. This is integer. I need to convert that to float, and then do a divide. So the value, if all were equal, is 3.5. I showed that I've genericized the plus slash. Um, And actually, when everything gets when everything is genericized, then this expression will be quite equivalent. It will be just the dupe, the plus slash, the swap, the count, and the divide. So, and that will be virtually identical in terms of complexity to the APL or the K. But I would say cleaner. Oh, and around, I decided that this is again one of those things about having such an open language. I decided maybe I'll keep this or maybe not, but might as well just do that. Make a float version of the count version. Um, so okay, we've got the mean, so forth, but so now what's the distance between 2 points? And one of the things is all of this, what's the distance? It applies in any number of dimensions, and that's about where I'll end this talk. But what's the distance between this actual 3, 4 and that mean, the 3, 5s? And this is
Bob,
where if,
sorry to interrupt. You got about 5 more minutes till we stop the recorder. You can, of course, continue after that. Up to you.
oh, okay, I knew that this is why I was saying it. It's going to be part 0. But there's the difference between two vectors. And actually, one of the things is, I guess most people here, virtually everybody knows that. But just going through the definitions of, well, variance is the distance. All of these, this is all about distances and square distance. Okay, the variance is the distance of the actual data from essentially this mean. It's a perpendicular distance, and per count. And I use that right here. So that's your the variance of just that single pair, and taking the square root. Okay, that's the oh no, that's the square. Oh, I do this, and there's our standard deviation. Um, and yeah, the variance. Now, the next step is going to get to. I mean, these are the most basic multi-dimensional algebra. Next step is because I want to get to correlations, normalizing to length 1, mapping to a unit sphere, and that's just dividing by the norm. So you go and divide by the norm, which calculated up there. And I made a word normed here to go and make it T1. Yeah, that shows that up here I went in and executed to go and get from the norm. T1 is T0 normed. And I'll do that also for this 45-degree line. And that's square root of 2. And so actually to get that, and you can see that's 1 over the square root of 2. So I won't go into covar. One thing that, oh yeah, let me go and show this working window and show this window where all of this is ups. Well, that's the window, and let me go and show the result. Yeah, here's this math, the whole math library, so you can go through. And a lot of these are converted rather directly from Arthur Whitney's K-math functions. But you can see covariance, correlation, so forth. And let me come down and, yeah, finish with this little example. I made the word normed. Do I still have my blah, blah, blah norm? Yeah, here's that. We got this is the line up through. This is the mean line, if you will. And in fact, actually, if you look at my logo, which I guess all of you've seen, which is a cube, the length of its main diagonal is the square root of the number of dimensions that it is. And yeah, figure out how many dimensions. So, oh, okay. We've got looking at we got our T0 and we've got this mean line. If we look at the covariance there, whoops, do I still have T0 around? Yeah, I do. Oh, forget that. Yeah, that's what I wanted. I don't know when they're going to be. Yeah, one of the points that I wanted to make, and this is really the end point that I was, making, but when you've got these normed, when you've taken your data and normed it, so it's sitting essentially on the unit sphere in however many dimensions. And then, well, this is the x-axis here. And doing this norm, this dot product, actually the correlation, this is the same as the correlation, is actually the cosine of the angle between two vectors and whatever your data is. And I'll just say that because one of the things is here we've got the 1 line versus the 1 0 line, and that's pi over 4. And just to show that, okay, that's 0.71. Okay, and what's the cosine of pi over 4? And one of the things again that is there, don't throw away the value, the splittability of RPN very easily. But do those match? Yes. Okay. So I just wanted to end with the correlation between two pieces of two sets of data. Because here we go to some. I got some random words, and in particular, I'm going to use randf.
Down there.
So
I'm going to
here,
in a few minutes.
a point in 30-dimensional space. It's limited to 0 to 1. And here's the average
So let's say I'll be back by
variance. And the final one, another point in 30-dimensional space. And here are those 2 points. And here's the correlation between them. And that's the cosine of the angle between those 2 points in 30-dimensional space. And last thing, my logo. Yeah, you can figure out how many dimensions that cube is. And you can then know what the length of that main diagonal is. And one last thing, which be part 2. This is actually from what would have been my dissertation And a great Professor Don Campbell actually paid to get this damn thing made. But we're going to be talking about the discrimination of patterns and holographic memory, and then get into, I mean, that's the fundamentals. This is starting to get into the math for AI and so forth, because AI is all about, in a sense, clumping these things together and then converging on, okay, these attributes and so forth. But actually, oh, and I also wanted to get into complex numbers, but that obviously I've got the marker there. This was as far as I was going to get. But it's interesting that complex numbers are quite easy to are really rotations in rotations, and are 2 by 2 arrays that whoops that anyway, I'm done.
All right.
All right, I'd like to thank Bob and all of the other speakers. I'd like to say that those ne'er-do-wells that are here today that didn't register for the meeting on MeetUp, you're ne'er-do-wells. What can I tell you? If you're watching this on YouTube, you can, if you're likely to see the meeting at some later time on YouTube, you can register for the meeting at MeetUp as long as it hasn't happened yet. And if you want to get the list, the agenda notifications, you can do that from MeetUp. But the more people that are members, the better we look. What was it, 374 members at this time? And thank you, Leon, for sponsoring our MeetUp participation. Leon Wagner of Fourth Incorporated. Leon Wagner is Fourth Incorporated. And I had one more thing I wanted to say, and damned if I don't remember it. We're going to head for Armadillo Willie's. If you live in the Bay Area, we're pleased to have you join us. This one's going to close, so it's our last time at the is it Los Altos, Armadillo Willie's. Any other closing comments, remarks, slanders, libels, rumors, gossip? Okay,
I'd
it's
like
so
a little.
nice to.
Was that worthwhile? I mean, was
It
that?
was.
Oh,
If I didn't feel it was worthwhile, I wouldn't schedule you, Bob. Thank you. Uh, if I didn't care for it, I wouldn't say thank you at the end.
One final comment. A real thing that makes CoSy unique is here. This is APL level succinct notation, and to be able to map that to the hardware implementation that was it's Chris talked about earlier is unique. You know, the APLs can't do it. They're closed systems that are based in C. So anybody who's got some value in being able to go and do their figure out their algorithms at this level and then map them to whatever comes along, that is a major motivation for this entire CoSy meander.
So I'd like to point out no major disasters yet this year, but it's only January. All right. On that cheerful note, why don't we stop the recorder, Brad?